Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
So, Linda, do you think a machine could predict hospital outcomes? Or I guess it's patient outcomes in general. I don't know. It's specific to a hospital.
Well, it's funny you asked. I just read an article about this.
Tell me all about it.
Well, I don't remember all about it. You seemed a little bit too interested there. But anyways, what it said is once you train these neural networks, they can catch things that humans don't catch, and they do it better than humans.
Yeah, that's definitely a possibility. They could catch things humans don't catch if they're able to maybe look at wider arrays of data or notice things in finer resolution that humans haven't learned or something like that. Also, they don't get fatigued, so the doctor, can't be maybe sick themselves or lazy or who knows what. So there are some advantages. But what do you think, who is scoring better, actual doctors or computers?
Computers. That's what the article said.
Well, that article is from the future then, because humans are still a little bit better at this time. But we're very much on the cusp of a changeover, it would seem.
Are you saying computers miss stuff?
They do not as good a job as doctors in general. In some very specific cases, maybe they do better. But we're making a lot of progress, and that's why I wanted to talk to Ed about Dr. AI, because I think it's a step in the right direction, doing some interesting things in this space. Why do you think a computer would do better than a person?
The article I read suggested that computers can process the data much more rapidly, doing large volumes and large amounts, whereas it would take months and months for human people to do it and to have peers review it as well. And then also it just seemed like the computers were able to catch things that humans weren't. Humans were catching other things, I guess, and computers were prone to catch other things, so they're just separate things as well.
So maybe we need the complement of these two tools. We need a human who also gets to look at a model's output and maybe synthesize the results in some way. Having not read the Dr. AI paper, what would you guess its success rate is at predicting diagnoses and time till they see the patient again?
Well, it's got to be more than 50%.
Well, you'd think so. Actually, 50% would be quite good because they're looking at a lot of different diagnoses. But your thoughts are on the right track. Yeah, it has to be better than random. Interestingly enough, we'll get into this a little bit. In fact, Ed points out to me that the baseline he uses is not random. It's actually what condition did they report last time? Because a good heuristic would be, well, probably you're complaining about the same thing again. So you have to beat that to be more accurate. But they measure recall. Recall is of the conditions people report, what percentage did they get? And they're getting about, depends, there's a couple of ways they tweaked it, but more or less 79% recall after 30 days. So that's pretty good in my opinion. I don't know if it's going to put the doctors out of a job, but it's definitely an interesting step towards this hybrid model of doctor-computer in the doctor's office. But do you think we'll ever eliminate doctors? Will one day you just plug in some sort of USB port and it scans you with your phone or whatever?
No, I don't think so. I mean, that's for diagnosing specifically. I mean, you still need doctors for now to do the surgery.
For now. Pretty soon they're going to be in the unemployment line, maybe.
Yeah, but then that'll make healthcare costs come down.
There you go. Well, this is actually a very complicated topic. We're going to cover this in a series of Data Skeptic episodes between now and the end of the year because the types of things we talk about on the show are very relevant in healthcare right now. We're undergoing a lot of changes, so I want to kick that off with today's interview, but I'm glad you're here to help me intro it, Linda.
I just thought of one more thing. I mean, if we can't even get self-driving cars passed and legalized, it's going to be a while before we get robots that do surgery passed and legalized.
Well, that's an interesting point, but hopefully when the data shows that something is better, then that will win out over people's superstitions. For example, most of the data on self-driving cars shows that they're actually much safer than human driving cars. That doesn't mean we should roll them out immediately tomorrow, but seems like we're going to have those. And as I've told you, I think my niece Noemi, who's 3 now, I predict she'll never be allowed to drive a car. It'll actually be illegal. But anyway, let's get into Dr. AI. Edward Choi received his master's in computer science and engineering from the Korea Advanced Institute of Science and Technology in 2009 and his bachelor's in computer science and engineering from Seoul National University in 2007. He is currently pursuing a PhD in computer science at Georgia Tech under the supervision of Professor Jimeng Sun. Edward's main research interests include predictive modeling, temporal modeling, and healthcare analytics, specifically using representation learning and interpretable deep learning for predictive healthcare. Over the past years, he has held research internships at Sutter Health, DeepMind, and more recently, Google Research. When he's not in the lab, Edward is a dilettante pianist, a low-budget traveler, a self-approved philosopher, and most of all, a gamer at heart. Ed, welcome to Data Skeptic.
Hi, this is Edward. Thank you very much, Kyle. Thanks for the invitation.
I think it's a great time to be a computer scientist and to be working in machine learning and deep learning specifically. Realistically, every field and industry can probably benefit from your work. What made you specifically interested in focusing on healthcare?
To be honest, healthcare was not my passion. When I decided to go to PhD, I was mostly interested in machine learning rather than healthcare. When I talked to my advisors, so Jimeng's son, Jimeng was my advisor who interviewed me for Georgia Tech admission, and I found out that he was interested in combining machine learning techniques with healthcare. And I liked the guy personally. I liked Jimeng, and I was hoping that I could work with him. And healthcare sounded like a very promising application, and I heard a lot of good stuff going on by the time 2014, and it was going to grow and grow as time goes on. So I thought it was a good time to jump into healthcare analytics. And I put some effort in it for a couple of years, and this is where I am right now.
When I hear discussions about healthcare, the acronym EHR, electronic health records, always comes up, which sounds like a good phrase to describe, generic medical data. Is EHR something more formal that has a really good schema, or are you dealing with a variety of different types of data and formats?
It stands for like a total data collection solution. It's not just a record of patients when he visited, what kind of drug he was administered, or what kind of diagnosis he received. It's more than that. It's like a complete record of everything that went on in the hospital. So not just structured data, but it has medical notes like doctor's notes, discharge notes, progress notes. It also has lab measures associated with the encounter. It's also the demographic information, the family history. It's total information package for all patients who went to the hospital. So it's actually a very, very private information.
Are there challenges then around getting access to the data you need because of, HIPAA or just general privacy issues?
I'm not really an expert in the legal aspect of EHR, but I did internship in Sutter Health for 2 summers, and we agreed upon having the data actually inside Georgia Tech server, but it took a long time to actually get it physically inside Georgia Tech because there was a lot of legal issues to be handled. Sure. And also the server had to be super secure, so it had to be behind like 2 VPN layers and such and such. So the time that we agreed to have the data inside Georgia Tech was in the summer, but the time we actually got the data was like 6 months later. So there's a lot of challenges in getting hands in the private data.
Yeah. That's an interesting discussion in and of itself, but it sounds like everything was handled very, with a lot of care and thought and legal concerns. So once you've got that data set, can you tell me a little bit about what you have to work with?
We didn't receive all aspects of EHR. So for example, as I said, EHR also contains medical notes, but since medical notes contain actual names of patients or doctors or like very characteristic symptoms of individual patients, so it's even more of a risk than compared to just diagnosis history or medication history. So what we had in our server in Georgia Tech was structured data sets. So it's when the patient visited hospital, what kind of procedure he went through, what kind of medication he was administered, what kind of diagnosis received, some demographic information such as ethnicity, jobs or age, date of birth, that kind of stuff. So that was pretty much it. I had those structured data. Mostly I used them to predict future disease or maybe recommend medications or future mortality, that kind of well-known problems in healthcare.
Well, let's get into some of the specifics there and the work you described in your recent paper about Dr. AI.
So Dr. AI was actually extended work from the first deep learning application that I did in 2015 summer. So what I did in the summer 2015 in Sutter Health is I tried to predict, given the patient record, encounter history, medication history, procedure history, my project was to try to predict the onset of heart failure diagnosis in the future. I thought it was a perfect opportunity to introduce RNN into it because RNN is also a sequential model. So that's what I did during the summer. And starting fall semester 2015, there was a postdoc in our lab. His name is Mohammed Taha Bahadori. I should mention his name because he's a very, very good friend of mine, a close collaborator. A lot of work that I've done is all through the discussion with him, and he's always in my papers, so I should mention his name. Taha thought it would be interesting to do a sequential prediction using RNN. So every single encounter, we try to predict what kind of medication is going to be prescribed, what kind of diagnosis is going to be received, what kind of procedure is going to go through every single encounter based on his entire history, entire encounter that he's been through before the current encounter. And then we do it encounter by encounter, or maybe time step by time step if you think about RNN. So that was our main objective.
So I know a lot of historical work trying to make predictions in healthcare has focused on single outcomes. Like we're going to build something that just predicts the onset of, one particular diagnosis or illness or something like that. Can you tell me a little bit about the motivation to generalize to a larger set of diagnoses that Dr. A attempts to tackle?
We wanted to be ambitious. We were thrilled by all the good news we hear from deep learning field, like how it's doing so well in vision, how it is tackling problems in NLP, natural language processing, how it's done great work in audio processing. So we thought it would be excited to test out the state-of-the-art RNN or LSTM sequential model. So we thought, why not make it ambitious and then just call it Dr. AI? And we try to predict everything that goes on in patient progress or patient trajectory over time. It was just an ambitious project, actually.
How do you guys compare your outcomes, whether today or what you think can be achieved long-term, to more of, let's say, a specialized focus? I could go build 10 classifiers that each individually look at one disease, or I could go the Dr. AI route and build a meta super classifier that tries to capture every technique and maybe can even see patterns across them. Does that, pulling it all together, present some advantages for cross-correlation and things like that?
Well, technically, it's not so different when you focus on a single disease and multiple diseases. So basically, in single disease prediction, you just have one class, whether it'll occur or not. So it's a binary classification. When you go full-blown like Dr. AI, you just have a lot of disease, like maybe 1,000 diagnosis classes. So it's a 1,000-class multi-label, multi-class classification. So technically, it's just adding more heads to at the top of the RNN. So whether you use sigmoid function or whether you use softmax functions, that's the difference. So I think it's more of your attitude when you focus on a single disease or when you focus on a lot of disease. When you focus on a single disease, you use the traditional sense. You study that disease in a very, very deep fashion. You understand the whole trajectory, what affects the disease, what kind of medication it is usually used to treat the disease, like the whole thing. But when you go full blown like Dr. A, you can't really, as a non-clinician myself, you can't really understand the whole 1,000 diagnosis classes. So you depend on the data. So it's a purely data-driven approach. So that is a route that we took. But traditionally, what you would do when you focus on single disease is you really work closely with a clinician, an expert in medical field, and then you understand and you extract relevant features from the record, and you make a very intelligent classifier. What we did is we dumped in a lot of data into RNN, hoping that it would figure out the correlation, as you said, correlation between a lot of diagnosis codes, a lot of medication codes, procedure codes, and then it would eventually figure out the complex relationship between diagnosis codes. So that's the route that we took.
So I'd like to talk mostly today about your work, obviously, rather than other techniques one might apply. But since the paper has such a, in my opinion, thorough background of different techniques and discussion as to why they're not as advantageous as your approach, could you touch a little bit about, some of the other techniques that have gone in the past, like continuous time Markov chains and things like that?
Before RNN, people used linear autoregressive models or Markov chains to deal with sequential data. And in a sense, I don't want to attack those techniques because they're still useful in their application. But RNN is more general because you take input at each time step, and then you also consider the history from your past time step, and then you combine them into a continuous embedding. It's a very expressive model. In hidden Markov models, you first need to define states that your model can be in. So you have to understand the problem, and then you have to define, I think I'll create maybe 12 states. So maybe in this state, the patient is having flu. In this state, maybe the patient has cancer. So you have to predefine the states to use Markov model. But RNN doesn't have like predefined human understandable state. It has internal representation of how things are turning as time goes on. So it's more expressive in that sense. So that's why we chose RNN. Before jumping into deep learning, I worked for a year using a stochastic process models. Specifically, I used Hawk's process. I'm not sure if you're familiar with it. It's a point process model, and what it does is it models the probability of events happening in the future in a continuous timeline, and it is the prediction is based on what kind of other events has happened before. So it basically considers all the events happened before the current time step that makes the model kind of slow. So it's a very slow training process compared to RNN. So we thought it was first time we tried RNN. So we were kind of focusing on what kind of benefit RNN could bring compared to previous work. So that was why we address a lot of previous works in the related work section.
And I'd like to get into a little bit about the details of the recurrent neural network you built. Can maybe to start with, you describe a little bit about the architecture, how many inputs you had, the nature of those, the hidden layers, so on and so forth?
We took all the diagnosis codes and medication codes and procedure codes occurring in our data set. So that sums about to 30K unique codes. We don't differentiate between diagnosis codes and medication and procedure codes. We just think of them as words in natural language processing. Like each word corresponds to each diagnosis or medication or procedures. We have 30K dimensional. We can express them as 30K dimensional one hot vector. So we have 30K dimensional vector where everything is zero except for one dimension where it represents which the dimension represents a certain specific medication or procedure or diagnosis. So that would be our input at each time step. And it won't be a one hot like in the natural language processing. If you process sentence word by word, you'll have single word occurring in a single time step. So it'll be a one hot vector. But in our case, we feed one encounter at a time. So in a single encounter, there could be multiple diseases, multiple medications or procedures in a single encounter. So it would be, we call it a multi-hot vector. I'm not sure if it's a technically correct term.
Makes sense, though.
Yeah, because a lot of things could be one and so most of the dimensions will be zero, but about 5 or 10 of them will be turned to one on average. So we call them multi-hot vectors. So each time step we feed multi-hot vector into RNN, and first we embed it or we project it into a lower dimensional space by applying fully connected network and then putting a nonlinear activation function. We shrink it down to typically 256 dimensions, huge reduction, and then we put that into RNN. So the size is, I think we tried 128, 256, 512, or maybe 100, 200, 300. So we search the hyperparameter space not too thoroughly, but in a space that made sense to us. I think it's around several hundred neurons in the hidden layer. And we also try to stack one more or two more RNNs on top of each other. So in an overview, there would be 3 layers of RNNs stacked on top of each other, or maybe only 2 layers. We found that 2 layers work pretty well compared to a single layer RNN. So that would be the RNN side. And then on top of the RNN, we would put softmax function on top of the hidden layer of the RNN so that we can make prediction at each time step. So the softmax function, if we are to do it in an ideal fashion, we would predict the entire 30K dimension again, because the input was 30K dimension. We would have to predict 30K dimensions to see what happens in the current encounter. But that would make the job of softmax too hard because it's 30K dimensional. It's a 30,000 class classification problem, and it's mostly going to be very, very hard for us naive softmax because a lot of codes are very similar to each other. Even in hypertension, there are different types of hypertension. And even in one diabetes, there are a lot of different varieties of diabetes. So it's mostly going to be very confusing for softmax. So what we thought is, why don't we group the fine-grained codes into a little more abstract concept? We used a coding scheme from ICD-9. So ICD-9 diagnosis code used 5 digits to encode each single diagnosis, but you could only use 3 digits to group them into a similar concept. So if you use only 3 digits, it'll be 1,000 categories compared to 10,000 categories when you use 5 digits. So that's what we did. We grouped diagnosis codes and medication codes using existing groupers so that we shrunk the output dimension size to like 1,000 dimensions. And it made the softmax job easier. It made the interpretation of the result easier for people as well. So that's what we did. So that's the entire architecture.
So on the input side, something that's really fascinating to me is how you did basically no cleaning or feature engineering. You said here are, the medicine codes or whatever prescription codes, as well as the, what the doctor assigned as a diagnosis. And there are no separations. They're just those one hot encoded, yes, this was present or not. And the very sort of almost magical quality of deep learning is that it does its own feature engineering. It kind of figures out which of those are important. So that first step where you go from, I think you said 30,000 possible inputs down to a few hundred is kind of like an embedding layer, I would guess. Is that what essentially happens?
Exactly. Yeah. Yes, exactly. So because my background is also, my background lies in natural language processing because that's what I studied in my master. And I also, during 2010 and 14, I worked in a Korean government institute before coming to PhD. And what I did there was also mainly text processing, POS, part of speech tagging or named entity recognition, like very classical NLP. I did that. So I come from NLP and I still try to follow what goes on in NLP. And these days, back in 2014, like there were like sequence to sequence models or using RNN on NLP was a very, it was a hit. So and they typically embed words into smaller embedding space, just like what we did in Dr. AI. So that's where we drew the inspiration. Because we have 30,000 dimensional input, we should shrink it down to a smaller latent space and then let the RNN deal with that.
When I look at the RNN you guys have built, if I interpret it correctly, there's really two objectives in the output. It's trying to predict the time until the next visit, as well as what condition might be in the next visit. Is that correct?
Yes, exactly, yeah.
And can you tell me a little bit about how you establish a good loss function to kind of balance these two objectives?
We didn't design a very intelligent loss function for this. Basically, we have a loss function for predicting the correct codes that's going to happen in the next visit. And we also have a separate loss function for the size of the duration between consecutive visits. So that would be just a linear regression. That spits out a single scalar value, which represents the duration or the number of days between visits. We just add those two functions to make a single loss function, and then we let the optimization algorithm take care of it. So we didn't put too much effort into it. And we actually found out that predicting the codes was working better than expected. But predicting the duration between visits was much harder than we expected. I mean, it was better than just random guessing, of course, but it wasn't doing well. Afterthought was it's obvious that it is hard to predict when the patient is going to visit the hospital. That depends on so many levels of factors, like the economic status, the neighborhood the patient is living in, whether he or she has a car, what kind of job he or she has, the income. I mean, a lot of things affect the decision to visit a hospital. Just based on the past record, I don't think it's a trivial job to predict when the patient's going to visit the hospital.
Yeah, there's so many confounding factors like whether or not they have to work that day that's just not available in your input data set. Interesting. How do you judge the accuracy of a model? Obviously, you can do your standard train test split and see how well it performed on your training data with a holdout set, but what do you benchmark against? Can you compare it to a domain expert or to another system that does similar predictions?
On this paper, Dr. A, we just did what you described in the first place, having a holdout data set and then doing a test run on that. So that was mainly our initial setup. Actually, I'm not sure if you're looking at the paper right now, but there's a table 3 that we asked the medical student to take a look at the result, and then he pointed out that some of them make sense, some of them don't, and we have that like a preliminary evaluation from medical student, but he's still a medical expert, so better than us. So he took a look at it and then gave us a preliminary or initial evaluation and said that this seems to work well, but we didn't thoroughly go through clinical evaluation.
Sure. Let's take a break from our show to talk about our sponsor for today, Periscope Data. Periscope Data is a great tool for data teams who want to rapidly go from SQL to charts. If that's not enough, they've also made it seamless and easy to do cross-database joins. Now, I'm not just talking about writing queries between two separate databases that might be hosted on the same server. No. Periscope data allows you to join tables in MySQL to a query in an entirely different Postgres database. The interoperability extends to Oracle, MS SQL Server, Redshift, Vertica, MemSQL, BigQuery, and others. So how do they do that? It all happens on their backend. They also have this great caching layer which you can configure, which centralizes all your data so that those queries run smooth and efficiently, as if you were joining two tables on the same database. Guys, that's tremendous. If you work with an organization that uses more than one of these types of databases, you really have to check out Periscope data. In just a few clicks, whatever results you got from that cross-database join of the two tables that were previously siloed and unconnectable, you can turn that result into a dashboard of visualizations and get it sent straight to your boss's inbox. Check them out today at periscopedata.com/skeptics. And what sort of, in terms of like if it's precision or recall, what do you look at when you describe the achievement of the model?
We looked at the recall because we thought mainly we try to predict everything that's going to happen to the patient when he visits. So we're going to predict diagnosis and medication. So we have to predict a lot of codes at the same time. So we thought recall is a measure that would best represent how well the model is doing. So we have like recall at K because we are predicting thousands of codes at the same time. So we have to take top 10 or top 20 or top 30. So we have a measure called recall at K. So recall at 10, recall at 20, recall at 30. And then, so that's what the table 12 of the paper describes.
Yeah. What kind of scores did you see achieved compared to what would be maybe random chance?
We didn't use random chance as baseline, but we have a very weak baseline, which is repeating the codes from the last visit. So if you had cold last visit, then we are going to, the most naive model will be, he had cold last visit, so this time he's going to have cold again. So it's basically just repeating what kind of codes were in the last visit. And that gave us the recall at 10, like, well, it doesn't even need recall at something because you have a fixed set of codes. So you don't need to cut off from like thousands of codes. So basically that gave us like 30% recall. But what we achieved is reaching towards, if we do like recall at 30, we reach like 80% recall. So it's compared to that most naive model, we're doing significantly better than just repeating what has happened in the past.
Yeah, so there's absolutely some knowledge gain in the learning process there.
Yeah.
What do you think about future investment in this? Obviously, you guys didn't have infinite money and infinite time. What could that be with, big grants and sort of stuff? Can we get that into the 90 range, or is there some boundary on just how predictable health conditions are?
Oh, I see. You mean like how far we can push the model to be so more accurate or more robust? Is that?
Yeah.
We focused on structured data only in this work. So that's basically just the codes that occurred in the past. But as I said, EHR is so much more than that. It has notes, it has demographic information, it has lab measures, and all those. I heard from a clinical expert that the gold is hidden in the clinical notes, not the structured data, because he said like somewhere like 70% or 80% of the entire information is described in the medical notes, and the structured data like this, like the ones that we use in Dr. A, it only represent like 20 or 30% of the status of the patient. So if we really want to significantly improve this type of model, we should dig into more modalities. We should use everything that we can get our hands on. Like notes is, of course, a must. And also lab measures like blood pressure checks or all those, continuous values from labs. That is also a must. And also demographic information is very helpful. Family history, that is also very important. But we didn't take any text-based resources into account when we were building this model. So that is where we should attack in the upcoming efforts.
One question does raise is how well the model generalizes. And I'm kind of unclear as to what I would expect. On one hand, people are people, and we're all the same species. So it seems like, we have similar medical records, but of course, family history, genetics, these sorts of things play a role. Of course, your training data biases what your model is able to accomplish. But can you tell me a little bit about the applications of transfer learning using Dr. AI and moving on to new sets of patient data?
Hospitals have different patients. So, for example, like Children's Hospital of Atlanta, they would mostly treat children. But like Sutter Health, they are more focused on like age from 40 to 80. The data that I received from Sutter Health was people from age 40, between 40 and 85 or 90, I think. So they have vastly different characteristics. So it wouldn't make sense to expect Dr. AI, this single RNN model, to do so well on all problems based on the so if the RNN has been trained on one data set, we cannot expect it to do well on all kinds of data set. Like it won't do well if Dr. A was trained on senior data set with senior patients, then it won't do well on data set with children. So that's sensible. Different size of hospitals have different size of cohorts. So some hospitals or so small clinics, they wouldn't have like huge data set that companies like Sutter Health has. So how about we train Dr. AI on a huge data set so that it's a pre-trained model, and then we retrain it or refine it on another data set that we are interested in. So we would train Dr. AI on tens or maybe hundreds of thousands of patients first, and then refine it or fine tune it with tens of thousands of patients that we're actually interested in, that we want to do prediction on, and see if it actually helps having a pre-trained model. So that's what we did in one of the experiments, and it has shown us that when you have pre-trained model and when you start from scratch and then just train in a small number of patients, compared to that, when you actually train Dr. A on a huge number of patients and then just fine-tune it with small number of data sets, the latter works so much better than just starting from scratch. So that's like one of the potential of transfer learning that we try to address in the paper.
Yeah, it's a very exciting area to me, especially because I think of so many illnesses where, because of their rarity, we have a small data set. If we could benefit from transfer learning, we could probably gain a wealth of knowledge about some of these more rare conditions.
Actually, so I have also another paper on that. So the paper was accepted to 2017 KDD. So the name is GRAM, so it's a graph-based attention model for predictive healthcare. So we just call it GRAM, like GRAM. But basically, it addresses the problem where it's hard for people to obtain a lot of data for people who has rare diseases. Even in large hospitals, like even when there are so many patients, only a very small number of subset of patients will have that rare disease. So in an absolute sense, it's hard to gain a huge volume of data that regards to that condition, or maybe some hospitals won't have huge data at all. So we try to incorporate medical ontology. So ontology, like how different diseases are related to each other, or how some diseases actually a child of another more abstract disease, just like ICD-9 hierarchy. So we use that as a medical domain knowledge and try to introduce that into making prediction when using RNN. So the RNN will use not only the past records, but it'll also incorporate medical domain knowledge such as SNOMED or ICD-9 or CCS, categorical. I forgot the abbreviation of CCS, but it's basically like there are a lot of different kinds of like hierarchies or ontologies. So the RNN will pull knowledge from that ontology as well as past records and make more intelligent predictions. So that was our main focus in the recent paper.
So if people want to learn more about Dr. AI and some of your other work, I'll have links to those papers in the show notes, of course. But there's an added bonus. I think people can go to your GitHub and see the source code for Dr. AI. Can you talk a little bit about what's available there, what people can run, and what's shared?
So I try to make public all the codes that I've used when I was writing papers. So I think currently I'm maintaining, I think, 6 different repositories. So most of them are written in Theano, except for one repository, which is called MedGen. It's generating medical patient records using general adversarial networks. So except for that, everything is written in Theano. So if people are familiar with Theano, then I think they can easily read the codes because it's not a long code, basically, especially for Dr. AI. What I did is just write gated recurrent units, which is another form of RNN. Mm-hmm. So I just wrote that and then just pre-process the data and then feed it into the RNN to make sequential predictions. So that's basically what I did. So if you go to the GitHub, I think you can easily search it. If you just search my name, Edward Choi, and Dr. AI, then you'll see GitHub on the top of the Google search page. So there I have Dr. AI, the source code, and then there's also a pre-processing script for Mimic. Mimic is a public data set. It's not a large data set, but it's one of the most famous public data set. It's a pre-processing script for that. So you download Mimic, and then you run that pre-processing script on Mimic, then you'll have a data set that is ready to be fed into Dr. AI to make the life easier for the users. basically using the source code and pre-processing script, you can train your own Dr. AI using mimic dataset and see how it goes.
I think those are two good steps for people interested in this field. Any conferences or anything like that you're headed to you want to recommend for in the near future?
I don't think I need to tell people that KDD is probably the biggest conference venue for data mining and knowledge discovery. So KDD is a very famous conference, and I'll be attending there to present my paper, Graham. But after that, there's a small conference called Machine Learning in Healthcare, which will be held right after KDD in Boston. So it's a small conference. It started like a couple of years ago, and it's a small community yet, but we are hoping that it would blow up to be a full-scale, like large conference, because I know that a lot of people are interested in healthcare, combining healthcare and machine learning together. So that's the main theme of the conference. So that's why it's called Machine Learning in Healthcare. So a lot of good ideas, good papers are presented there, and I'm also going to present my MedGAN paper, which is generating patient records, as I said. So I'll be presenting that paper there. So it's August 18th to 19th in Boston. So if people are interested, they're welcome to come there. I'm hoping that I would meet a lot of interesting people, talk about a lot of interesting work there.
Excellent. Edward, thank you so much for coming on the show. So to wrap up, maybe I can ask you one more just sort of question that's a unbounded prediction. I'm sure you may have heard that relatively recently Jeff Hinton made this statement that we should consider not training radiologists anymore because it's a long training period, and by the time you're out, the deep learning systems will be better. In fact, Christine, who wrote the bio for you for the show, she wrote a recent blog post on dataskeptic.com all about this. Do you have any thoughts on that? Is deep learning going to put a lot of doctors out of business?
Well, first of all, I have to admit that I haven't heard what Dr. Hinton said about the radiologists, but I don't think maybe on very simple day-to-day jobs could be handled efficiently by machine learning, like deep learning. And also, I think especially in imaging business, like analyzing MRIs or X-rays or CAT scans or PET scans, I think neural nets can give a lot of helping hand to doctors in analyzing it. But I don't think we are quite there yet to drive doctors out of business. I don't think it's that simple, because doctors, they draw knowledge from biological, chemical, and also like they learn a lot of stuff to understand what goes on behind the scenes, and that's where they draw their knowledge from. But machine learning models, they draw their knowledge from pure data. So unless that gap is somehow shrink in like next few decades, I don't think doctors will be driven out by machines that easily. I mean, they take a whole different approach, and it's an approach that has been like certified that has been proven to be working for a very, very long time, for the entire human history. So I don't think just a few years of deep learning like hit is going to change the landscape of medical business significantly. I don't believe that's going to happen anytime soon.
Well, again, Edward, thank you again so much for coming on and taking the time to share a lot of your research. This is really interesting work, and I'm eager to follow the rest of your career.
Thank you very much for the invitation. I had a great time talking to you.
All right, take care. One last thing before we end the show. I've got an article coming out in the latest issue of Skeptical Inquirer magazine. It's called The Missing 411 Conspiracy, an Investigation. Let me give you a little quick background on this. Somewhere on the internet, I bumped into this idea called the Missing 411 that this author David Paulides had started talking about. Paulides believes that people are disappearing from national parks and other wildlife areas at an alarming rate under unusual circumstances. And it's really draped in this air of mystery and kind of conspiracy and, something's not right here. But it also made no specific claims. It wasn't saying, there are being alien abductions or something wacky like that. It was very open about what the claim was. I got into this thinking there would be a cool statistical project, or, we could talk about how this sort of data is tracked or where to get it or what kind of biases have to be accounted for. I don't know. I just thought there'd be an interesting stat story. So I started looking into it. Turns out I didn't see anything interesting to say that related to statistics or the data, but nonetheless I did this little skeptical investigation and tried to give a fair shake to this missing 411 idea to see if there was anything to it. If you want to hear my thoughts, again, those are in the latest issue of Skeptical Inquirer magazine. That's volume 41, number 4. I'm looking at it right here. A bunch of other great articles in here as well. And listen, one last thing here. I've been meaning to say something about this for a while. I get some feedback from people about the show saying like, what's the whole skeptical thing? Don't skeptics, spend their time not believing in aliens and Bigfoot and all kinds of kooky stuff like that? What the heck does that have to do with data science? It's a distraction. Why do these things mix sometimes? And look, even the claims in AI and in machine learning that we might look at and say, I'm skeptical of this idea. Can that model achieve what they really say it does? Those sorts of things, they're more like claims of plausibility. Someone says, it's 80% accurate the way we predict what customer's going to churn out. Really, 80%, you're that accurate? You're probably more like 70, but maybe you got something. Okay, let's talk. And we all have that sort of skepticism. This thing says it scales infinitely. Well, there's some exaggeration there. I'm sure it's a great product. Let's talk about how it actually works. Skip past the marketing BS and learn the real details. And when, you're skeptical in that way, it can feel like you're just fine-tuning a claim that's more or less correct. And that feels about 1 million miles away from the people who actually claim that they believe the Earth, get this, in the modern era, they believe the Earth is flat still. The Flat Earth Society is a thing, and it's probably not entirely a joke. So here's the deal. There is a gamut. Sometimes I'm going to be too skeptical for you, sometimes not enough. But that's the data skeptic journey. And critical thinking and logic are, you have to admit, absent in many important areas of our society. That's not a political statement. That's not an attack on anybody. Just in your own mind, think about those words. Does everything that you know of work in a logical, rational way? And I'm sure you'll come up with some situations where you think it doesn't. So if there are people who will believe anything, despite much evidence to the contrary, all the data in the world is not going to help them. The best models we create aren't going to matter if they're disposed of without inspection or consideration. The power of data science, not only do the kind of techniques we use need to be looked at skeptically, as the models say it does what it does, but our ability to make these useful things to our society stands entirely on a foundation of a society that thinks rationally, logically, and skeptically. And when people believe anything despite all evidence to the contrary, well, skepticism at all levels. Sorry for preaching for so long. But yeah, check out my article if you're interested.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.